Hello everyone. So today I'm going to present my thought process for problem 6 for this IMO. Well, it's past the IMO season. This problem, I think it is very beautiful and also very hard. I'm very happy that I can solve it well. It took me a lot of time, which is why I made this video. I solved it, in fact, when I was in a short vacation, when I do have the time to think about it for a few days. And I do think that there's no way that I can solve it during the IMO. Like, even if you dump all the 4.5 hours to me, assuming that I can get problem 4 and problem 5 instantly, there's still no way I can get everything within the contest time frame. Well, realistically, I might be able to get 1 point by showing some of the properties that I will present later. So yes, it is fair that I do regard this as a boss fight. If you look at the statistics, well, only 5 people got everything, and there are only a handful of people who can get like some really comfortable partials from like 3 to 6, and more people got 1 point, but a vast majority of people got 0. Well, I'm also very happy that Malaysia managed to get 2 points in total on this problem. So with that being said, let's hop right into solving the problem, and this is how the problem would look like. So let's first describe what the problem is about. So this is basically about a functional equation. So let's say you have a function f from rationals to rationals, and then it satisfies this property. So for any x, y that is rational, you have one of the two conditions hold. So either you have f of fx plus y equals to x plus fy, or f of x plus fy equals to fx plus y. So yeah, and then the task right now is how many different values can f of r plus f of minus r take when r is considered across all rational numbers. So yeah, so basically the number of the different values that this f can this f can take, and then you want to see like how what's the maximum you can achieve. Okay, so we all know that this problem is about a functional equation. Well, quoting from one of my teammates, Siu, functional equation is basically just trying to plug certain specific values and see what you can get out of it. Well, unfortunately, this is a bit trickier because it gives you two conditions for each pair, but only one of them is guaranteed to be true, and you don't know which one is that. So in other words, the evil thing about this problem is the or condition over here. So yes, this is basically the devil. Sorry, it should be like this. Yep, the evil part is here. Well, nevertheless, we can still think of what are the things we want to get out of from all those all those plugins. So usually it involves something like trying to find f of x naught for specific x naught. So well, here things that it means that you want to find things like f0 or maybe f1, f2, etc. maybe. And then the other thing could be that prove something like injective, surjective, etc. Okay, and all right, sorry. And then here again we do know that this thing the having this or can make things complicated because you have so many cases. but we can still find something that is easier to correct. So for example, if say like x equals y, right, then both of the conditions point to f of x plus fx equals to f plus x plus fx. So that means this is a fixed point. Now what if v is such that f of v equals to 0? Okay, we do not know whether this v exists, which means that we do not know whether 0 is a value of f. But if this v is in this condition, then we have f of v plus fv equals to v plus fv, and this is v, this is just v, so this is just fv equals to 0. So that means f of, sorry, that means that v has to be 0 here. So that means that if there's any number that maps to 0, then that number must be 0. So f of non-zero is non-zero. Okay. Now, is it the case where fv that there's such a number v? Well, it turns out that the answer is yes, but proving that is actually a bit tricky. So for one thing, you can you can first show that, oh, okay, this function is injective, which indeed it is injective, but it does take it does take a bit of creativity to notice that. So I will show you my way of doing that, which basically takes you a long route before proving that. So long story short, if you can show that it is injective, then well, given that f0 equals to f0 because of this thing, means that f0 equals to 0, right? Okay, now say w equals to f0, then f of w equals to w. Okay, now let's fix x equals to w, y equals to minus fw. Okay, so what does that mean? So x plus fy equals to w plus f of minus fw, and then fx plus y equals to fw, but then you know that but then you know that this one is just w minus fw equals to w minus w, which is just 0. So we have either f of x w plus this thing equals to 0, or f of 0, which is basically just w, equals to w plus f of minus fw. So this thing is 0. Okay, so that means that in either f of w plus f of minus fw equals to 0, or f of minus fw equals to 0. So 0 is indeed a value of f. So since f of non-zero equals to non-zero, we know that f of 0 has to be 0 here. Okay. All right. So now what does that? Now how can we efficiently plug things back? Well, what? Okay. Now think of this. So we have fx plus y, and then fy plus x. Think of what happens if one of them is 0, right? So let's say if this is 0, then you either have f0, meaning 0 equals to fy plus x, or f of fy plus x equals to 0. But we know that f of non-zero equals to non-zero, so that means that this has to be 0 either. So f of y plus x equals to 0 here. Now fx plus y equals to 0, so y equals to minus which means that we have this one, f of minus fx equals to minus x. Okay, so with this, you can easily show that f is injective plus bijective. So this is an important part. Okay. Now, from what I heard, getting this itself is worth 1 point. So we have successfully laid the groundwork, and then now we can now we can go on to explain a bit more. Okay, so now let's continue our progress for this problem 6 from the IMO. So as previously stated, we have shown that f0 equal to 0, and also like injectivity and surjectivity of the function. So now how do we proceed? Well, first of all, we still recall that we have this thing f of fx plus x equals to f of x plus x. So meaning that these are some of the fixed points of f. So now one of the tricks of this problem turns out that we want to determine or maybe find some properties of the fixed point. So let's say L equals to the set of all x such that fx equals to x. So why the name L? Well, we'll show later that this set behaves like a lattice. Okay. Now, why do I say that? So first of all, we see that 0 is in L because f0 equals to 0. Okay, this is what we have proved before. Now, what are the other things that we want to establish? So one thing that you can guess is that this L is closed under addition and also negation. Why is that true? Now, if x plus x and y are both in L, right? Then if fx plus y equals to x plus fy, that or f of x plus fy equals to fx plus y, both of them would mean f of x plus y equals to x plus y. So meaning x plus y is in L. Alright. Now how about if x in L, right? Then how about minus x? Well, we recall that f of minus fx equals to minus x. So this becomes minus x. So minus x also in L. Okay, now what are the things that we want to find? Well, now it will probably help to visualize this this so-called the lattice set. So you would expect that, okay, so let's say this is let's say we have this graph, and then we have 0, and then this is these are the lattice, and then we want to have some function such that it will pass through here, 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 and then say for example this point at here is over here, then you will expect that. So let's say this is like, I don't know, say this is, for example, say this is 1, I don't know, just making up some number. This is 0.2, and then this is, I don't know, like A, and say this is like 1.2. You might expect that, or maybe guess that these two have the same gradient, meaning that, so if this is A, then you have this is like 1 plus A over here, and then say if this is 2.2, and then this is gonna be what, 2 plus A over here. So that means that it is kind of like some sort of like fx equals to what, like x plus some periodic function. So you might have something like over here, and then it shoots up, but the pattern should look the same. Now this is something that you could guess about the function, but then you still have to prove it. So how do we continue with this? So in order to do this, we still rely on the whole notion of the lattice point. So recall that we fx plus x are all in L. Now what's going to happen next? What if fx plus y is in L? Okay, so recall that f is injective, This is pretty important. Okay, so f is injective, meaning that we still want to write this condition out. Okay, so if this is the case, right, then this is just the same as fx plus y. Now, if this is true, then what happens is that this inside, because it's injective, must be the same as fx plus y. So in either case, both point to fx plus y equals to x plus fy. So meaning that fx plus y in L means that fx plus y equals to x plus fy. And also, since fx plus x is in L, as we have shown, this this thing holds when x minus y is in L. Why do I say so? Because fx plus y equals to fx plus x plus y minus x. So this is in L, and then x minus y is in L, so y minus x is just a negation, it's also in L, and then they are close under addition. So this whole thing is also in L. Now, are we ready to show the lattice thing that we have drawn before? Well, I suppose so, because now we want to also formally write what we claim. So that means that we want to claim that if fx is in L, right, then y anything f of x plus y equals to x plus fy. Okay. Proof. So the trick here is to consider this thing, f of x plus y plus fy equal is the same as what? X plus y plus fy. Why is it so? Well, because this thing x plus y is y plus fy is in the lattice. Now, how do we continue from here? So because this thing is in the lattice, right? So because x plus y plus fy is in lattice, we have already shown that this thing is the same as f of x plus y plus y. So meaning that you just like swap this x plus y and y, right? So this means x plus fy equals to f of x plus y. So basically, we just have basically we just have this thing, this property, except you substitute x plus y into x. Okay. And finally, what happens to arbitrary x and y? Now, this is actually getting more important here. So we have spent quite some time in digging the different properties, but we have not actually addressed like what the problem asks us to do, aka find the distinct value of fr plus f of negative r. So we are not quite there yet, but then we can do something that makes us to be one step closer. So how do we do that? So first of all, we notice that f of x plus fy, this is the same as f of x plus, it should be something like y plus fy plus x minus y. Okay. All right. So this thing is the same as y plus fy plus x minus y. Okay. So now we have two cases. We call that f of xy plus this, or x plus y equals to fy plus x. Okay. So because that we can write this thing as what? Because see we have f of x plus fy equals to y plus fy plus x minus y. So let's just copy this whole thing over here. Sorry, this is wrong. This is supposed to have f of x minus y here, right? But regardless, this is the same as this one, and similarly this is the same as this one. So if we rearrange the whole thing, we get fy plus f of x minus y equals to fx, or fx plus f of y minus x equals to fy. So this will hold true for all x and y that are rational. So yeah, this is the second part of the groundwork that we do. We are just basically using some properties of the fixed point set, or aka the lattice set that we're interested in, and we establish some of the functions of the properties which we think will be useful in the rest of our analysis. Okay, now the task, we already established all those different things about the function f, including this thing that becomes very, very important. Now you want to know like how many elements can this have? Fr plus f minus r for r. How many elements? Well, one thing we see that setting r equal to 0 means that fr plus f of minus r equals to 0. So 0 must be in it, and then we are interested in seeing whether this thing can contain some other elements, and if so, like how many different other non-zero elements that it can have. So as it turns out, from this thing, like the blue thing that I just highlight, that you can guess that, well, there shouldn't be too many of those. So let us actually show that. Now I have to admit that before I actually get to solve this problem, I've already glanced through, picked through some of the comments from out of problem solving, and they say that, hey, this thing can have at most 2 elements. And I also get to see get to glance through just one shadow of an example that they show, which I will try to recover and motivate it later. But still, once you get this thing and combine with some of the intuition that you'll see later, that you'll see that, yeah, it makes sense to guess this answer. So we want to claim that this thing is less than or equal to 2. Okay. Now, how do we show this? So one thing that we can show is that all the non-zero elements are the same. So how do we do that? So consider f of r1 plus f of minus r1, and then f of r2 plus f of minus r2. Then show that either they are the same or one of them is 0. Okay. Before that, we want to go back to this one. So we have this OR condition, fy plus x minus y equals to fx, and then fx plus f of y minus x equals to fy. When does it become an AND condition, meaning that both of them has to be true? So let's copy this whole thing. Okay, when is this an N? Well, if both of these were to be true, then you see that fx minus y plus fx y minus x equals to 0. So if this if this one, this difference, they add up to 0, then both of them, it's either none or both of them are true, but since we know that one of them has to be true, so both of them has to be true. And conversely, if this is not 0, then only one of them can be true. Okay, so how do we go by this? So then, okay, so since we have R1 and R2, then we naturally just change this into the R1 and R2 form. Okay, so case f R2 minus R1 plus f of R1 minus R2 equals to 0. So what happens if this thing is equal to 0? Now, well, we have that both of these are both of these have both of these have the whole. Now, you might think that, okay, since we are interested in R1, R2, and also like minus R1 and minus R2, right? How about we substitute this thing into it? So minus R2 plus, well, yeah, as we have assumed that R1 minus R2 minus R1, and then our f of R2 minus R1 plus f of R1 minus R2 is 0. So this all actually becomes an n. So what we need is just these two things. Right, because we know that both of them have the whole, then we don't really have to be in the dilemma of like, oh, like what happens if this is true, that one is not true, and blah blah blah. Yeah. Okay, so that would mean that f1 minus f of R2 equals to f of minus R2 minus f of minus R1. Well, they are both the same as this. In other words, f of R1 plus f of minus R1 equals to f of R2 plus f of minus R2. Okay, so we are done with this. Okay, now let's assume that f of R1 minus R2 is not the same as f of R, sorry, not the same. They add up to non-zero. Okay, so that means that one of them has to, one of these two have to hold, but then they cannot they cannot both hold. Or this one, but not both. Okay, now since R1 and R2, they are symmetric, we can say, okay, without the loss of generality, we assume that, yeah, this first one is true, second one is false. So let's do that without. And then this one. Okay, now the trick now is to just, shuffle things around and then see what we can get, that we can get with it. So indeed, if we say say x equals to R1 minus R2, and then y equals to R1, and then you consider this thing. Right, you consider just like that's just moving things around, then you basically get things like f of R1 minus f of R1 plus f of what is R1 minus R2 minus R1, so that this gives you f of R, this one, or f of 1 plus f of r2 equals to f of r1. But we already know that this is not true, or rather assume that this is not true. So this one has to be true. Okay. Now, can we still keep moving things around? Well, yes, you can. So say here x equals to r1 minus r2, and then y equals to minus r2, right? Okay, now we'll just skip the step and say then say that yeah, we have like either f of minus r2 plus, so y is f of what f of y is this, and then f of x minus y, r1 minus r2 minus yeah, plus something equals to, okay. All right, sorry, I guess I should have did yeah, I guess I should have done something different. All right, so never mind. So f of our one is here. Oh, okay. All right, sorry. That was some like technical, technical disconnect. So okay, so we have, so let's say x equals to r1 minus r2, and then y equals to r1 y equals to minus r2. Then you get this thing plus f of r1. Actually, it should be minus r1, or f of minus r2 plus f of r1 equals to, okay. Now we know that this one is this one holds. So now we have again. Now we have two cases. So either again we have two cases. So again, now the question is that whether this one is an or, but whether it's an and or not. So if r of minus r1 plus r1 equals to 0, then we have an and condition. Okay. If it's not equal to 0, that means that f of r1 minus r2 plus f of minus r1 is not equal to minus r2. Okay. Now, how do we keep boomeranging things around? So yeah, so now let's try to highlight all these conditions. Yeah. This one and also this one. Okay. So just now we just now we already have this and minus r2 and minus r2 over here, and this is r1 and r2 minus here. So let's see what happens if we bring this back here. So here, so according to what we have, we can just keep, again keep shuffling things around. Or okay, we know this is false as per our assumption, but here, yeah, this is r1 minus r2 is here. r1 minus r2, and then okay, minus r2, and then this is minus r1. Okay, so this has to be true. So what are the so in the end we have this. Okay, now you can ask okay, whether we want to just keep moving things around, or do we stop at one point. What we need to do now is to collect what are the identities, the true identities that we have, and then collect them. So the first one is the first one is this one. The second one is this one. And then the third one, yeah, I'll just write it down. Yeah, but you can see what we have here, meaning that f of r1 minus f of r2 equals to f of minus r2 minus f of r1. Well, these are the same as f of r2 minus f of r1. So that means that f of r1 plus f of minus r1 is indeed f of r2 plus f of minus r2. So basically we have just shown that for any r1 and r2, either those things are the same, or f of r1 plus f of minus r1 equals to 0, or the other one is 0. Hence, this thing cannot be more than 2. Well, all you need to do is just to compare like every single pair, and you show that okay, this thing the sum is either 0 or all the same non-zero numbers. Okay, now this is the pretty much a big step. So we still want to find whether we still want to determine okay whether this is 2 or it can be or it can be reduced to 1. So yeah, that will be the next section. Okay, so as I said before, so we have already shown that the size of this guy cannot be more than 2. But this is not enough to solve the problem, because we need to either show that we can keep improving the bound to maybe 1, or we can show an example where we can achieve 2. Now, just to say a note, where if we want to just give an example of this as being 1, right, then it is easy. Then you know, like we have like f of x equals to x satisfies the condition. Now, what happens if we want to show that that is equals to 2? Can we have such an example? Well, the answer turned out to be yes, but then it is a bit tricky on how you want to construct such function. So in order to do that, we want to make sure we want to go back to some of the first principles, aka what are the things that we have shown. So we see that the set fixed points behave like a lattice. So meaning that it's like closed under plus and negation, and then we also know that 0 is in the lattice point. Well, so we can guess that how about setting this lattice point as an integer? Well, not an integer, the set of all integers, meaning that we need to have f of integer equals to x. And then we also need to make sure also that fx plus x is also an integer. So meaning that, you know, like things like, you know, like meaning that 0.1 says that f of 0.1 has to be some integer minus 0.1 and that stuff like that. So again, we want to like turn into visualization. Say this is 0, and then say like this is 1, right? So you have like 1 over here. So this is lattice, this is lattice, this is lattice. So now you have this weird phenomenon where on average it seems like things will have like things have greater than 1. Let me actually move this down here. So it looks like everything should have greater than 1. But if things have greater than 1, right, then you don't get you don't get this fx plus x has to be an integer anymore. So in a sense, if you want some of the continuity, then it actually, locally speaking, you need to have something that is that has like greater -1. Okay, something like this. So say like if say fx equals to minus x for some of the neighborhood, then yes, you do see that fx plus x equals to 0. It is gonna be all flat. So what does this mean? So this means that if you want to have some piecewise continuity, so to say, then this piecewise continuity plus x, right? It better stay constant. So can we actually construct something like this? And also I should also mention that we need to have f of say 1 plus y equals to 1 plus fy. That one we actually need to have. So this is something that we have shown before. Okay, so meaning that if it goes down like this, then this one here, it also has to go down like this. So what can we do here? Okay, we did not say that we cannot have any jump, right? So let's actually do that. So let's say that we at some point say like, I don't know, say this is like 0.7 ish, or just any number. We have a jump here. We just have a jump here, and then make sure that things are still continuous here. Again, we did not show that this function has to be continuous, but just for the sake of construction and making things easy, then we need to have some jumps over here, and then say here, and then if this is 0.7, this had better be 1.7, and then you have some jumps over here. So you ended up having something like this. Now the next thing is to see whether we can plug things back. So for this purpose, let's say let's say like let's say 0.7 is it's w, where aka some threshold. So what is this function actually? So this function is actually, I will just say it out, it's the same as the floor function of x minus, see the floor function, and then minus the fractional part, plus 2 times whether this floor function is greater than a threshold. Okay, right. So we want to plug things back and see whether this works. Now, of course, if you have seen like our problem solving, then you probably already know like, yeah, what are the functions that would that will work. And in fact, there's this w that would work, one particular w that would work, but not all of them would work. So then let us just try to do the dirty work. So say f of x plus y. So okay, again, this one we will just write it as the floor plus the fractional part. This one is just the floor plus fractional plus 2 times an indicator of whether x is greater than w, where, well, w is our threshold. And same thing, okay, now we want to see whether one of these would hold. Which I guess we can just write something like this. Yeah, just copy it. Okay. Now, how do we write this down? So, well, better not forget this thing. Okay, plus this 2 times okay, I should really say what this notation means. So this notation means that it will be 1 if this condition is true and false 0 if this is not. Okay, now we can all agree. First of all, we can all agree that if f of n plus y equals to n of plus fy, this one holds true. We can all agree that. So what we can do now is to move these things out over. So this we just have something like so yep, and then we want to see whether this is the same as this guy. Okay, and then we just cut this off. Okay, and yep, and then similarly we can do this do this for the other side. Okay, now one thing for sure, if say x and y belong, say like x and y is an integer, that means that these two must hold simultaneously. These two, yep, and then these two are the same, so this one becomes 0, and then f of 0 becomes 0, equal to 0, so our condition holds automatically. So therefore we can just say like what happens if, so this is a pass. So what happens now if like, okay, what happens if x is an integer? So x is an integer, that means that this is not this is not going to pass. This is not going to pass. And then this one we just have some and then this is just this is just going to be 0. So this both of this can cancel out. Now what does now this one just becomes negative f of y. Sorry, f of minus f of the fraction part of y plus where the 2 times the indicator of like whether this is greater than w. However, this matches exactly this term, so this also pass. And then same thing, we know that if y is an integer, this also pass, right? So after dealing with all those edge cases, we can now assume that we have something like this. So meaning that both of them are not an integer, and also neither of them is an integer, and also like the difference is not an integer. So this is the more general case. So we'll now deal with it like separately. So now the condition becomes whether this is true. And similarly, similarly the other side, but then with all the variables all the variables shuffled. So yeah. Okay. Okay, now here comes the slightly tricky part. So because what the fractional part of y minus, so this thing is greater than 0, but this is less than 0, right? So how do we write things in a more efficient, more like efficient way? So this one, it turns out that this is just minus the fractional part of y minus x plus 2 times plus 2 times this one. Whether this one is greater than 0. Okay. Now this one is slightly trickier because we have like this one, like x is less than y, right? So we do have something. So the floor function is actually -1, -1, and then minus. Minus what is this? Like x minus y plus 1 actually. So you actually have like two, like -2 here. Okay, so sorry, this is not 0. This should be w. Okay, so long story short, like when the fractional part of this is y minus, just the fractional, the difference fractional of y minus fractional of x. This one, the fractional part is fractional of x minus fractional of y plus 1 actually. So if we want to just like if we actually want to like rearrange this whole thing, right? Now this what this becomes is this. So here so here we can just like take things off, and then what we have here becomes okay. I'm just pacing here just for some self-reference. Yeah. Okay, and then similarly we can have something like this one for the next set of equality. And do we have a, but this is a, yeah, yeah. Now bear with some of the bad math over here. This is it's a plus, yes, there's a plus here, but then there's a -2 divided by 2, so it's a -1. Okay, check. Yep, so this seems to be the thing that we want to show that, well, okay, either one, for any x and y, one of them will be true. Okay, now what happens is that if this is less than or equal to w, then same goes to this too. Why do I say so? Because this one we have already shown that the fractional part of, assume that x fractional part of x is less than or equal to less than the fractional part of y. So first equation all becomes 0. Okay, so then the first equation is basically taken care of. Now what happens if x is greater or equal to w? Now the fractional part. So if the fractional part of x is greater or equal to w, right, then same goes to y. Sorry, it should be greater than. And then x minus y plus 1 is greater or equal to x minus 1 plus 1 is again is then greater than w. So second equation becomes 1 plus 1 minus 1 greater or equal to 1. So this is true. So both of them pass. So now you'll see when would it fail. So meaning that x less than or equal to w, but y fractional part greater than w. So that means that if we substitute this thing in, then you get something like this is 0, this is 1, and then this is 1, this is gonna be 0. So is it actually true that both of them can is it actually possible that both of them can fail? Well, the answer is yes. So all you need to do is just this 0 and this is 1. So so accordingly, we have already shown that so this is the only condition that where it can fail. And okay. Now, can this actually happen? Well, the answer is yes, unfortunately. So well for w, what you need to do is to say like, okay, let's say this is w over here, so y is just tiny over little bit over w, and x is just like tiny little bit below w. So yeah, unfortunately this is where it fails. And does it mean that we have to find a new set of solution? Well, not really. What I did not say is that here this happens when w is strictly between 0 and 1. But what if say that what if we set a w equals to 1, right? That means that we don't really have to care about all those indicator things, because well, none of them matter. So they'll just all be just all be 0. So yeah, that is where things that is where things could work. So meaning that what we have is that fx equals to floor of x minus the fractional part of x. So this is the function that we that will make the condition work. And then do something, and then what is fx minus plus f of minus x? So it will be 0 if x is integer. You can show that this is actually minus 2 if x is not an integer. So the construction is complete. So yeah, with this construction, we can be sure to say that yeah, we have solved the problem. And yeah, this is problem 6. It took me a few days, well, not continuously, because I'm just like, sometimes I just thought of this problem when I'm bored. Yeah, but yeah, that's but you can appreciate how hard it is, and then how much genius it is in order to solve this during the contest. Like, well, for sure, if you just throw me into the IMO, then I don't think I can get the whole thing within 4.5 hours. Yeah, that would be a pretty big challenge, and therefore like kudos, like salute to those people who actually accomplished that. Like even getting 1 point, like getting that the injectivity, surjectivity, whatever that conditions, that actually is not going to be easy.